so I have also posted this on our website where the homework assignments are, and the posted one is a PDF which also has answers at the end. So after working these out, you may want to check the answers. That's where you can find the answers. I just put the answers. I didn't work them all out. So if you have questions about why this or that is the answer, let me know. I'd be happy to help out. All right. Anybody have any questions about the test? I think everybody knows what's up at this point, but it's going to cover all the topics through number 20. You should bring your checklist with you, but don't write stuff on the checklist. I don't want you to write notes, because you're not supposed to use notes on the test, but it should just have some things checked off so that you know which ones to do and which ones to not do. Anybody got questions? All right. Yeah, let me know if you have sort of mathematical questions that come up. I will try my best to help you out before the test. The last topic that we had, and on the list, it's number 19 and 20, were about increasing and decreasing. I have one more sort of subtopic of increasing, decreasing to talk about, and then we'll move on to something truly different. But this has sort of fancy sounding topic name, relative extrema. Relative extrema. This is about extreme points on a function. This is something that we have talked about before, but not using this kind of terminology, but this should look fairly familiar. Kind of, at least. Anyway, a relative, I'll tell you what it's all about first. A relative maximum, when it comes to relative extrema, there are two types. There's relative maximum and relative minimum. A relative maximum is a point on a graph whose y value is greater, that's what makes it a maximum, greater than the nearby values. That's called a relative maximum. So what it looks like on a graph is something like, if that's a function here, I see actually two different relative maximum points. So the word maximum refers to the fact that the y value is higher. So this one over here, that one is a relative maximum because its y value at that point is higher than all the nearby y values. And I see another one over here. This is also a relative maximum because the y value is higher than all the nearby y values. All right. Now this one, its y value is not higher than the ones all the way over here, but at least for the ones nearby, it is higher than all the other ones. That's what the word relative means. It means only the ones nearby, not all of them overall. All right. So those 2 points, this and this, those are relative maximum points. All right. And you can also talk about a relative minimum point, and you can probably see which one it is on the graph. That would be a point which has y value lower than all the nearby points. So I'll just write that down. A relative minimum is a point with y value less than the nearby values. And I see one such point on this graph. It's down there. All right? This is a relative minimum. All right. So these points, I mean, we have talked about the importance of points like that before. Those kind of bumpity points, either the tops of the hills or the bottom of the ditch. Those are called relative extrema. The word extrema is the plural of the word extremum, which is meant to be like minimum or a maximum. Either one of those is called an extremum. So a relative, this is a weird word, but a relative extremum is a point that is either a relative maximum or a relative minimum. A point that's either a relative maximum or relative minimum. It's like a Latin form of the word or something. Extremum. It means these are sometimes called extreme values. Extreme meaning either the biggest or the smallest, either minimum or maximum. So a relative extremum is a point that's either a relative maximum or relative minimum. And the name of the subject or the topic that I wrote right at the very beginning, relative extrema. This is the plural of extremum. You with me here? These are weird words, but they're not all that complicated. So a relative extremum is just one of these points, either one of the tops of the bumps or one of the bottoms of the bumps. All right, those are the relative extrema. And they are important in the real world. Like, if these represent sort of profits of my company over time, this one is important because those were the best profits we ever had, right? This one was important because this was sometime in the past when, at that time, it was the best ever, but it became even better later on. And then this was sort of a temporary dip in the profits, which eventually got better, all right? But anyway, if you care about things in the real world modeled by functions, probably these points are important for some reason or another. They represent the best times ever or the worst times or whatever. Not necessarily the best time ever. This is not the best time ever. It was, in those days, it was the best times nearby, but eventually we got even better. All right, anyway, these are the relative extrema. Now, if you're looking at a graph, it's always easy to find the relative extrema. This is the typical question that I would ask you in homework problems or test questions. Find the relative extrema. On a graph, this is easy. You just look for all those bumps, the top of the bumps or the bottom of the bumps. Easy on a graph. So for example, if I have some kind of graph like, sorry. How about that? I went kind of off the side there, but if you're looking at this graph, where are the relative extrema? That is just all the relative minimum and maximum points. They're just at the tops and the bottoms of these little bumps. So there's one there. There's here, and here, right? I think that's all of them. And you can say easily which one is a maximum and which one is a minimum. The ones at the top are maximum. So this is a relative maximum. This one also is a relative maximum, and this one. Those are all relative maximum points. I don't like the way I drew those lines, the arrows. All right, those are 3 relative maximum points, and then there are 3 relative minimum points. Here, here, and here, right? All right, they are easy to identify on a graph, and we don't really have to talk very much about that. Although one thing to notice is those relative extrema, this is kind of an obvious fact once I tell you, maybe even obvious before I tell you, the relative extrema always occur at the critical numbers. Remember the critical numbers, that's when the derivative is 0 or derivative does not exist. F prime equals 0 or F prime does not exist. Right? And it's not a coincidence that all of these extreme values, the minimum and the maximum points, they do indeed occur at places where the derivative is 0. Like right here, the derivative is 0. That's because the tangent line would be flat horizontal. Or like right here, this weird pointy point, that's a place where the derivative does not exist because there is no specific tangent line here because it has a little pointy point. But all these other ones, the derivatives are 0, all right? The relative extrema always occur at the critical numbers. And that means, even if I didn't show you the graph of the function, if I just told you a function, like wrote down an equation, you could still find these points because we already know how to find the critical numbers, right? You would set the derivative equal to 0 and solve for x. So we can find these even without looking at the graph. And that's the more interesting kind of problem that I would ask you to do. Just looking at the graph is very simple. We can find these even without looking at the graph. All right? It's actually almost the same as the increasing decreasing business that we have been talking about. That also involves finding the critical numbers. And then you look at the signs of the derivatives with the increasing decreasing thing. We can find these points even without looking at the graph. But so really the only sort of new question that arises is how to tell which are maximum versus minimum. You can find these points because they are the critical points. But if you're not looking at the graph, how do you know which one is a maximum and which one is a minimum? That's really what I want to talk about today, because the other part is the same as what we've already been doing. How to tell which are the maximum versus the minimum. I'll tell you sort of the short answer now, and we'll say more specifically later, but you look at how the signs are changing, and I will clarify this. I just want to do an example. You will see what we do at the end is look at how the signs are changing. That's the way that this goes. But let's just try to demonstrate by an example here. Your job in a typical problem about this would be to find all relative extrema for this function. Let's say 2x cubed minus 3x squared minus 72x plus 15. How about that? This is my function. I want to find all relative extrema for this function, and for each one say if they are minimum or maximum. All right? We will get several answers. We're going to say, x equals 1 is a minimum and x equals 3 is a maximum. Something like that is what the answer looks like. All right? Anyway, we're going to begin just like we did the increasing decreasing thing, which is why it looks different on the surface, but really the method that you use to solve this is exactly the same as the increasing decreasing business. So we start by finding the critical numbers. The critical numbers. That is, you take the derivative first. So f prime of x. This is a fairly simple function to work with. To do the derivative, it's a polynomial, so I just go down the line there. I go 6x squared minus 6x minus 72. I think that's the derivative. Anybody remember how this goes from last time? What should we do next? Yeah?
Simplify.
Yeah, simplify as much as you can. In this example, that would be factoring. So one thing I can do is factor 6 out of this whole thing. Everything is divisible by 6, so I pull out the 6. It'll say x squared minus x minus 72 divided by 6 is 12. So it's like that. I would like to factor even more. Can we factor that other piece? Anybody see how to factor the other piece? Yeah?
X equals 3, x minus 4.
I like that. X minus 4 and x plus 3. Yeah. Okay, and this is as simple as this is going to get. So that is my derivative. Excellent. What do we do next to find the critical numbers? Take the derivative, simplify as much as you can, and then what? Yeah? Set the derivative equal to 0. That's how you find that's what the critical numbers means. It means when the derivative is 0 or the derivative does not exist. In this case, we don't care about the dne part because there's no denominators. So I set this whole thing equal to 0. That means, since it's factored already, we set each individual piece equal to 0. So I go 6 equals 0, x minus 4 equals 0, x plus 3 equals 0. And then you solve each of these for x. The middle ones, you add 4, you get x equals 4. The last one, you subtract 3, you get x equal minus 3. And 6 equals 0, that just doesn't give you anything. You can't solve that for x. There's no x in there, so we don't get any critical numbers from that portion. We just get these two critical numbers. All right. This is all exactly the same as the increasing, decreasing stuff that we did last time. Next, we should make the chart with the signs of the derivative. So I label these 2 points on a chart here and here, and I'm interested in the signs of f prime, that is positive or negative for f prime. And this is the part where you plug in numbers in each of those regions, right? These points divide the line into 3 regions. And I choose something less than negative 3, I'll choose negative 4. And I'm plugging into, copy that box you see at the top right there. This is what I'm plugging into. Just put that, maybe right over there. F prime of minus 4 is 6 minus 4 minus 4 minus 4 plus 3. That's positive. Negative 4 minus 4 is negative 8, so that's negative. And then negative 4 plus 3 is negative 1, which is negative. This all gives me a positive because I'm multiplying those things. So it's negative times positive. Positive times negative. So anyway, that over there, positive, right? In the middle, choose a number between negative 3 and 4. I will choose 0. So I plug f prime of 0 is 6. 0 minus 4, 0 plus 3. That's a positive, a negative, a positive. So this is negative. Negative in the middle. And then on the far side of the 4, I'll choose 5. F prime of 5. 6 times 5 minus 4 times 5 plus 3. I believe all of those are positive. Positive, positive, positive. That means this one over here, positive. All right? Now, if I were asking you about increasing, decreasing, you would be done at this point. You would say it's increasing over here. That's negative infinity to minus 3, increasing, and also increasing 4 to infinity, and then decreasing minus 3 to 4. That's in the middle. All right. What about the question that I'm asking here is, what about the relative extrema? So they are these points, negative 3 and 4. The only thing that we need to worry about is, for each of those, are they a minimum or a maximum? And that you can tell by looking at these signs. So I'm going to copy this down just so I can talk about the signs here. I dropped it. The signs. I lost part of the 4. For example, look at negative 3, right? So near negative 3, it goes increasing and then decreasing. I mean, if you look sort of at this chart from left to right, we have increasing followed by decreasing. That means if you can imagine what this function looks like, it increases until it gets to negative 3 and then decreases again. So is that a point? Is that a maximum or minimum? I think it is a maximum. It's at the top because what this says is it increases until you get to minus 3 and then decreases again. So that means it goes increasing, then decreasing. So this point near negative 3 is at the top. So that means x equal minus 3 is a relative maximum. Increasing and then decreasing means it's a maximum. And this other point, 4, decreasing and then increasing. That means it goes down until you hit this point and then goes back up, which means that point is a minimum. So near, I'll just write the same thing, near 4, it goes decreasing, then increasing. So x equal 4 is a relative minimum. All right? So the procedure really is the same as increasing, decreasing problems. It's just at the very end, you have to know how to read this chart in a different context, right? You look at how is it changing from plus to minus or minus to plus. Now this, what I said here, actually there's a name for this general idea here, and I'm going to write it a little more formally down here. This is called the first derivative test. Derivative is what I meant to write there. The first derivative derivative test. The first derivative test, actually there is a second derivative test, which we're going to do eventually, but this is the first derivative test. What it says is, the first derivative test is all about identifying minimum versus maximum. That's the point of the first derivative test. And what it says is, if f prime goes from plus to minus, then it's a relative maximum. That's what we said before. If f prime goes plus to minus, that means the function is going up until you get that point, and then it goes back down again. So that point is a maximum. If f prime goes minus to plus, it's a relative minimum. That is, if it decreases down to your point and then comes back up, that's a minimum point. And then there's another, and sometimes it is possible if f prime goes plus to plus or minus to minus. This doesn't happen in most of the examples we look at, but it is possible that this can happen. Then, what does that mean? That means the function goes up to this point, and then immediately after that point, it continues going up. That means actually this point is not at the top of the hill. It's in the middle of the hill somehow. So that means it's not a relative maximum or minimum. All right, the picture for that would look something like a point which somehow it flattens out there, but it doesn't, that's not actually at the top. It just keeps going up afterwards. All right. In that case, the first derivative test, the conclusion is this point is not a relative maximum or relative minimum. All right. That's what the first derivative test is all about. It is how to tell if something is a maximum or a minimum. All right. I got one for you all to try. So you will do, this is really only describing the very last step of what we just did. The rest of it is this exact same as the increasing, decreasing thing. So you find the critical numbers, you make that chart with the pluses and minuses, and then you analyze the chart according to this simple rule here. All right, so yes, I want you to try find and identify, by identify I mean say if they're minimum or maximum, the relative extrema for this guy here. X cubed minus 6x squared minus 36x plus 4. See how you like it. I hope you can remember all the steps. You should start by taking the derivative and simplifying as much as you can. Take the derivative. You should, in the program, you should keep it like put 3 for the numbers. Yep. Yeah, so now you should make this chart where those two numbers are. Just hit the number. This should be 3. Yeah, I don't know what.
Oh.
3 comes down here.
Yeah. Okay. Is that would be my 2.
The 12 is right because it's the 2 multiplies on the 6. Yeah. Doing good? Mm-hmm. All minuses. Doing not all minuses. Should be plus minuses. No, this is just. But you're plugging -2 into x, right? So this 3 stays over this. Yeah, right. Because it's. Yeah. But this is not your final answer.
No.
Yeah, so it's this is the rule. So for instance here it goes plus and then minus. Plus and minus means it goes up and then back down, so that point is at the top.
And then if it was just plus, that's not.
That would be no nothing.
Okay. But even if it goes from next to plus, next to that, and then plus, would it still just be since it's
Well, you look at each of these points individually. So you say -2 because it's plus minus. -2 is a maximum, but then this one because it's a maximum. This maybe it should go plus minus plus in this case. I think because that number should be increased.
Yeah.
Okay. All right, let's talk about these. It looks like people are doing pretty well here. So I will just go through real quick. You begin by taking the derivative. I go 3x squared minus 12x minus 36. Now I want to factor and simplify as much as I can. So take the 3 out first. What remains is x squared minus 4x minus 12. And then that part I can factor. So it says 3, I think minus 6 and plus 2, right?
Yeah.
3 minus 6 and, 3 times x minus 6 and x plus 2. Right. That's my factored form. Now we set this equal to 0 and solve for x. It says 3 equals 0, which is no solutions. X minus 6 equals 0, which is x equals 6. And x plus 2 equals 0, which means x equals -2. So I make my chart here. My 2 critical numbers are -2 and 6. And then I'm going to plug in values in between into that box right there. So here's my f prime is 0 here, 0 here. F prime of, let's pick -3 on the left side. It says 3 times -3 minus 6 minus 3 plus 2. This is positive, negative, and negative. So that over there is positive. I hope I'm doing okay so far. Point in the middle, let's choose 0. F prime of 0. I go 3 times 0 minus 6 times 0 plus 2. That's positive, negative, and positive. So it's negative in the middle. And then on the right side, I will choose x equals 7. F prime of 7 is 7 minus 6, and 7 plus 2. That's positive, 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 positive up there. So I hope this is what everybody got so far. Yeah?
Maybe you put the -3 in next to that prime in parentheses to start off.
Yeah, these 3 points you have to choose, so you think of these two numbers divide, this is the number line. They divide the number line into 3 regions, and you just have to choose one number. It's your choice, but choose one number from each of those 3 regions. So for the region on the left, I choose -3, just because it's the most reasonable number to choose, in my opinion. Yeah, and then in the middle, I pick 0, just because I like 0, and then over here, I pick 7.
Thank you.
Yep. Anyway, what's my final answer? The whole point of doing all of this for the signs or whatever is to be able to say for these numbers, are they minimum or maximum? So x equal -2 is a relative. Is it a minimum or maximum? You look at the signs here. This says positive and then negative. That means the graph, if you can imagine what the graph looks like, it looks like that. It's going up and then going down again. And so this one is a maximum. And the other one is a down followed by a up. That means that one, that number 6, x equals 6, is a relative minimum. That's how we do it. All right. Any thoughts about that one? So these relative extrema problems, I hope that you agree that they are basically the same as the increasing decreasing thing. It's only at the very end how you say the answer. Instead of saying I have increasing, then decreasing, then increasing, I say this about relative maximum or minimum. So the way that if you look at like the checklist of topics, this is not on the list anywhere, relative extrema. This is just, I consider this to be rolled in as part of the increasing decreasing stuff. So on the test this week, I won't mention relative extrema, but in the future tests, the increasing decreasing questions might be about this. It's really the same procedure. It's just a different way of answering at the very end. All right. I hope that's okay with everybody. Excellent. I had just one more of these to try. The one that we just went through, would fall under the category of easy one because it's a polynomial. Let's just try one that is harder because it's not a polynomial. So let's do same thing, find and identify the relative extrema. For this here, x squared e to the x minus 3. All right, this is a harder one. This will be good practice for the test. You might expect to see one like this in the increasing decreasing section for number 20, the harder one. Let's see if we can do it. What makes it harder is this function is harder to find the derivative, just from the very beginning. What I see here, when you think about taking the derivative, first of all, you have -3 at the end. So what I'm looking at is 2 things that are being subtracted or added together. They're subtracted. And the second is just a constant. So that means since they're just 2 things that are added together, we just consider each one separately. So I need to do the derivative of this part and then also the derivative of this part. Can anybody say what's the derivative of -3?
0.
It is 0, yeah. So when you take the derivative, this -3 just has no effect on anything. All right, I'm just messing with you. This -3 does not affect anything. Really, what matters is this part right here. And for that part, we need to use one of those rules. Anybody got a feeling about this one? Yeah?
Isn't it e to the x equals e to the x?
Okay, so this is the derivative rule for e to the x, which you definitely need to know. The rule is derivative of e to the x equals e to the x. I was thinking of one of the other, we also need to use one of the other rules. Yeah. Yeah, the product rule, because what I see here is 2 things that are multiplied together, right? X squared is the first one and e to the x is the second one. So we are going to use the product rule, where when it comes to the second part, we use this e to the x rule. But anyway, so that's how we do it. The derivative, I do the product rule. It is the first thing like it is times the derivative of the second thing. And like he said, the derivative of e to the x is e to the x. Plus the second thing as is e to the x times derivative of the first thing, x squared. The derivative of x squared is 2x. So that's the product rule. And the -3 just doesn't do anything because it's a constant added onto the end. All right. Okay. What should we do next? As always, we should try to factor and simplify as much as we can here. And what I see is two things added together. There's this guy and this guy. In terms of factoring, they both have e to the x as part of them. So I'm going to factor e to the x out to the beginning. What remains is x squared from the first part and 2x from the second part. I'm starting to feel a little bit better about that. And I think actually you can further factor this thing here. Can anyone say how do you factor a little bit more here? Yeah?
Take out x.
Yeah, you can factor out x from that. So this is as good as it gets. E to the x, and then what's left over is x plus 2, right? That is my fully simplified formula for the derivative. Okay, from now we are going to continue the same steps we did last time. So we find the critical numbers by setting this equal to 0. All right, f prime equals 0. That says, as usual, we just have to set each little part equal to 0. E to the x equals 0, x equals 0, x plus 2 equals 0. And then solve each part. Actually, the one in the middle is already solved for x. X equals 0 is a critical number. On the right, I get x equal -2. What about e to the x equals 0? There was a sort of a special thing to remember about those. B and E, yeah. Someone's giving me the thumbs down. This right here, there are no solutions. That's because, I hope you remember this slogan, e to the x is always positive, never 0. So it's not possible to get a solution from e to the x equals 0, because e to the x is always positive and never equal to 0. All right? So my only critical numbers then are 0 and -2. Let's make the chart. 0 and -2. I guess -2 goes on the left. I'm going to plug in to the derivative. The derivative is this thing here. Try and drop it at the bottom there. A little higher. All right. We're going to plug values in. Again, you choose the values however you like. There should be 3 numbers, 1 from each of these zones. So on the left, I'll use -3. F prime of -3. Plugging into the box, it says e to the -3 times -3 times -3 plus 2. I'm replacing x with -3. And then what are the signs of each of those parts? What's the e to the -3? Is that positive or negative? It is positive because I just said a moment ago, e to the x is always positive no matter what the x is. Even if it's a negative x, e to the -3 is positive. How can e to the negative number be a positive number? It's because remember, a negative exponent means 1 over e to the 3, and that's positive. So anyway, positive. -3, of course, is negative. -3 plus 2 is -1, which is negative. So that is a positive on the left side. In the middle, I will pick -1, I guess. F prime of -1. I get e to the -1, -1, -1 plus 2. This is positive, negative, and -1 plus 2 is +1, which is positive. So it's a minus sign in the middle. And on the right side, I will use x equal 1. So f prime of 1 is e to the 1, 1, 1 plus 2. Those are all positive, positive, positive. And so positive. All right. We're basically done here. The final answer is about extrema, right? So I say x equal -2 is a relative something or other, and x equals 0 is a relative. What do you say for -2? Give me the thumbs up for max and thumbs down for minimum. I see the thumbs are up. Overwhelmingly up. Yeah, this is a maximum, the first one. That's because the signs go positive and negative. That means the function goes up and then back down. So that's the top of the hill. And the 0, it's going down and then back up, so that's the bottom of the hill. So this is a relative minimum. That's my final answer. I hope it makes sense to everybody. This one was a little hard just because the function was weird, but it's the same procedure. Anybody got thoughts about that? All right. Excellent. We have about 30 minutes on the clock, and I think that's enough time to say a little bit about the next thing on the big old list. So this was the end of increasing and decreasing, right? This is the relative extrema, which is the same procedure, really. It's just you say the answer in a slightly different way. What I want to talk about next, remember I said that, we talk about the first derivative test. There is a second derivative test. And it's not called the second derivative test because it's like the second test. Actually, there's a thing called the second derivative. I want to talk about that. Can you believe it? The second derivative. I never said this before, but actually, the whole time here we've been talking about the derivative. Actually, we've only been talking about what we call the first derivative. There are other ones, like the second derivative. This will blow your mind. Actually, it's not all that mind-blowing, but the second derivative, it's written like this, f prime prime. We say f double prime. This is called the second derivative. And what does it mean? This will sound kind of stupid, but it is actually useful for a lot of things. It's the derivative of f prime. So the second derivative, it means, I'll say it this way, to find f double prime, you take the derivative and then you take the derivative again. That's what the second derivative means. Yeah?
Is this going to be on the test?
No, not this time. It will next time. Such a cliche question, man. I get it, though. Actually, I could throw it on the test just because it doesn't matter if you get it wrong, right? You might get it right. Is it better if I just put stuff you never heard of on the test? You might just answer 0, it might be right. Probably not. I don't think I'll put it on the test, but it will eventually. Anyway, to find the second derivative, you do f prime first, and then you take the derivative again. Take the derivative again. That's the second derivative. All right? This is just a thing, a fun thing you can do with your friends late at night, I guess. Take the derivative over and over again. It is actually useful for something, though. I'll tell you what it's useful for in a moment. But let's just, as an example, if I have f of x, it's x. Let's say x cubed plus 4x squared minus 7x plus 6. That's my original function. Find the second derivative. Really, there isn't a good way to do it all at once. You just do the first derivative first. So that is the ordinary derivative. This is an easy function to take the derivative of. 3x squared plus 8x minus 7, right? That's the derivative. If I want the second derivative, you just do it again. So f double prime x is 6x plus 8. That's it, right? That's the second derivative. In the case of a polynomial, it gets simpler every time. So actually doing the next derivative was easier than the first one that we did here. That's not always the case, though. Here's another example. Sometimes it can get more complicated every time. For instance, how about e to the power x squared? E to the power x squared. Anybody know how to find the derivative of that? The first derivative? It will, of course, involve this derivative of e to the x rule, but it's a little more than that. This would make a cute little question for the derivative of exponentials portion of our test. Anybody feeling cute, want to say? Yeah?
Do you take the 2 down and make it like 2x?
Not quite. So what you notice, what's interesting about this is you have extra stuff up top. I know you just felt cute. I'm there, man. you have this extra stuff on top, right? So what do you, there's one of these rules about what you do when you have something, but then some other stuff on the inside. That's the chain rule. So what that means is we use this rule to handle the outer portion, which is just the e, and then separately you multiply times the derivative of the inside, which I think is what you were saying. The derivative of the inside would be 2x. So in this case, we do the e part first. Using this rule, the derivative of e to some power is just the same answer again. So I get e to the x squared again, and then by the chain rule, I multiply now times the derivative of the inside of the exponent, which is 2x. So that was the chain rule. And using the e to the x rule, where you get the same thing again when you take the derivative. All right, anyway, that's the first derivative. What if I want the second derivative? I have to do the derivative again. And actually this time, the next step, I have to use one of the other rules. What do I have to do for this one? Yeah, this is now a product. It wasn't a product before, but it is now. And so when I do this step, we have to do the product rule. So I go the first thing like it is, e to the x squared, times the derivative of the second part, derivative of 2x is 2. And then plus the second part like it is, 2x, times the derivative of the first part. And actually that now is the same as the thing that we just did. So the derivative of the first part is, again, using the chain rule, e to the x squared times 2x. So that's the second derivative here. So the moral of the story is sometimes the function gets more complicated every time when you take the derivative. Sometimes it gets less complicated, all right? All right. Now, I don't know if anyone's thinking what I'm thinking. If you want, you can go crazy with this, and you can keep on taking the derivative again and again. Is there such thing as the third derivative, the fourth derivative? The answer is yes. I mean, you got to decide how you want to spend your time, but you can, if you want to, take the derivative repeatedly. Those are referred to as the higher derivatives. And they, to be honest, are not that useful for much in the real world. Beyond the second is quite useful. The third, less so. I think I've never in my real life seen anybody talk about the fourth derivative in the context of the real world. So we're not really going to do this very often, but you can, if you want to, do what they call the higher derivative. So here's an example. If it was something like x to the 4 minus 7x cubed plus x squared plus 3x plus 10. This tends to be easy for polynomials. I can do the first derivative. Just do the derivative. I get 4x cubed minus 21x squared plus 2x plus 3. I hope that this also seems easy to you. I'm just doing the derivative of a polynomial. That's the first derivative. What's the second derivative? You just do that again. So f double prime x would be 12x squared minus 42x plus 2. Right? I multiplied 21 times 2. That's the second derivative. The third derivative, you do it yet again. So this we write with 3 little primes, and this is 24x minus 42. Right? Could you do the fourth derivative? Yes, you could. So when it comes to the fourth derivative, usually around this time people start getting tired of writing all the little primes. It's hard to read. At this point, usually people start to write it that way. So a little 4 in parentheses. The parentheses there are just so that it doesn't look like f to the 4th power, which is not what we're talking about. We're talking about doing the derivative 4 times. So this one would just be 24, I guess. It's the derivative of the previous one. You could do it once more. The 5th derivative of x would be 0 now. And then actually, you could continue doing the derivatives, but they would all equal 0 forever after this point. You just get 0 every time. All right? I'll just say, etc. Okay, these are called the higher derivatives. You find them by just taking the derivative over and over again. Now, what is any of these things useful for? Like I said, the 4th, 5th derivatives, they don't tend to be useful in the real world. I'm sure they are in some kind of super abstract physics or something, but in ordinary parlance, you never really have a cause to talk about the super high derivatives. But the second derivative is actually, it does come up fairly often in real life. So just to talk about what it's supposed to mean, this is the rate of change of f prime, right? because it's the derivative of f prime. This is the meaning of the second derivative. So it's really sort of, it's a rate of a rate, because f prime itself is the rate of change of something. So this is how fast is the rate of change changing, which sounds pretty nonsensical, sort of abstract. But actually this does come up in real life. For example, the classic example of this is in physics. If you're talking about the physics of motion, if you have a function f of t, if f of t is the position of a moving object over time, position of an object. So at each time f of t tells you the position of something, then anybody recall what's the interpretation of f prime of t in that situation? This would be the rate of change, how fast the position is changing of an object. Yeah?
Velocity.
Yeah, that's the velocity. This is just how fast the object is moving through space, right? So f prime of t is the velocity. That is how quickly the position is changing. That means the velocity, how fast it's moving. I meant to say, if f is the position, then f prime of t is the velocity, and f double prime, that means how fast is the velocity changing. And there's actually a word for that everybody knows. What is that?
Acceleration.
Yeah, that's the acceleration. So f double prime of t is the acceleration. And this is obviously useful in the real world. So the second derivative is actually something that matters in certain types of applied problems. I mean, sometimes in some other situations, the second derivative might not be very interesting, but it definitely is interesting in this kind of physics of a moving object. And actually, in this case, there's even a word for the third derivative in this case. In this case, the third derivative, f triple prime, is how fast the acceleration is changing. This isn't something we often talk about, but the physicists do talk about this. And there's, anybody heard of this before? There's a name for that. This is called, I'm not making this up. This is called the jerk. It's called the jerk. I will explain why. You have to be looking at me. In real life, if you're like in a car that has a high speed, actually you sitting inside the car, you don't feel the speed of the car in your body. If you look out the window, you can tell you're going really fast, but it doesn't have it's not physically experienced by you. If the car is accelerating, you do this, right? You can feel acceleration. Or if the car is decelerating, you do this. What about the jerk? This is about acceleration changing rapidly. That means something like the car is accelerating really hard and then suddenly decelerating really hard and then accelerating again. What do you feel like then? You do this. That's why it's called the jerk, because it makes you jerk around. All right. The jerk is something that is harmful to people. You know, this is how you get whiplash in a car accident. It's not from the deceleration. It's actually from a deceleration followed immediately by acceleration in the other direction, because you're being hit from the front and then hit from behind or something like that. Or like this is what makes you, if you're holding a drink on an airplane or something, if the airplane is accelerating, you can kind of just sort of lean back without spilling your drink. But if the airplane is jerking around, then you will spill your drink. So people driving planes and trains also, they don't try to minimize acceleration, but they do try to minimize jerk. This is why. These are the people who care about the jerk. Most ordinary people don't care so much about it, unless you're in a car accident or something. Then the jerk is dangerous. This is, anyway, that's the third derivative, which we're not really going to talk about. We are going to talk about the second derivative, though, which in physics represents the acceleration. It represents other things, though, in other areas of life. F double prime is how fast f prime is changing. You occasionally hear people talk about this in real life, in politics or economics or something. Like I can remember actually when I was in college, I think it was my junior year my parents got a letter in the mail about the tuition for next year. So the tuition increases every year, as it always does. And this year, my parents got a letter that said, we're very sorry to say, unfortunately, the tuition is increasing this year, which, like, okay, everybody knows that's going to happen. But they said, but here's the good news. The good news is the rate of increase of tuition has decreased. Huh? What they mean is the tuition is increasing this year, but it's not increasing as much as it did last year, right? But actually, if you think about in terms of rates of change, they're talking about the rate of the rate has gone down. So that statement, if you were to express it mathematically, would be a statement about the second derivative. They're telling me the tuition is increasing. That means the first derivative is positive, but the rate of increase is decreasing. That means the second derivative is negative, which I suppose is some kind of good news. But yeah, that's the second derivative in real life. Whenever you talk about someone, this is true if people talk about like the rate of inflation is increasing or the rate of inflation is decreasing. This is about a rate of a rate. So these things they do come up in the real world. What I would like to discuss for our remaining 15 minutes is how do we see this on a graph? Right? Everybody knows f prime represents the slope on a graph, right? So it's fairly easy to look at a graph and you can visualize about the f prime. You certainly could tell if it's positive or negative based on is the slope positive or negative, right? F double prime represents what? That's what I want to talk about for our remaining 15 minutes here. Can you just look at a graph and tell me something about f double prime? Is it positive or negative or what, right? How to approach this? So let's think specifically about what does f double prime greater than 0? This looks like, what does it look like? The second derivative being positive means the first derivative is changing in a positive way. So this means f prime is increasing, which is to say the slope is increasing. That's what it means to say the second derivative is positive. It means that the first derivative is itself increasing. Another way of saying that is the slope is increasing. So for instance, what does a picture where the slope is increasing look like? It would look something like maybe this, right? That is a picture where the slope is increasing. So on the left side, the slope is very small, like close to 0. And as you move to the right, the slope increases, all right? So this is a picture of what it looks like when the second derivative is positive. This kind of a shape. Or there's other ways that the slope could be increasing. This is a little weird, but here's another example when the slope is increasing. Not that. This. Now, if you don't think too hard, you might think, isn't the slope decreasing here? Here it's really steep, and here it's not so steep anymore. But actually, the slope here is increasing because the slope here is steep and negative, whereas here it is close to 0. So what we have here is the slope is very negative becoming 0. That still counts as an increase, right? Something which is very negative becoming 0. That's an increase. So here is also a picture where the slope is increasing. It's going from negative to 0. That's an increase. Or something which is kind of a combination of those two pictures. And this is the way that I usually think of it, actually. Something like that, right? Here we have something which on the left side is negative, and then it becomes 0 in the middle, and then positive on the right side. That's increasing throughout. Goes from negative gradually to positive. Yeah.
If that's like, if this is how f double prime being greater than 0 is represented, if f double prime is less than 0, is it like concave down? Like, is that what that
Yes.
means?
Yeah, it's sort of all of those, but upside down. Would be what that looks like. Yeah, I'm going to say that in a moment. But so I would summarize all of this as being really the first two ones that I drew are just kind of like two pieces of this one. I would think of them all in terms of this one. So in general, f double prime greater than 0 has this shape. it looks like that. All right? It might look like only one side or the other side, but generally speaking, f double prime being greater than 0 is like this. And this, I think of just the way that I remember this. This is like the smiley, right? This is the smiley. And that means the second derivative is positive. And the other way is the frowny, and that means the second derivative is negative. That would be the same thing, but upside down. This shape, the official name of this is not smiley. This is referred to as concave up. That means it has this sort of U shape or smiley shape. That is technically referred to as concave up, but I usually just do this with my hand or think of the smiley, all right? So that's what f double prime being positive looks like on a graph, and I should just say the other way around. F double prime being negative has the frowny shape. So that is the shaped, same but upside down. All right, this is the frowny. And I hope it makes sense. We should just say, this, remember, f double prime being less than 0, it means the slope itself is decreasing as you go left to right. And that's definitely true here, because here the slope is positive, then becoming 0 in the middle, and then becoming negative over here. So that is decreasing, going from positive to 0 to negative. That's decreasing. All right, and this is referred to, the official name of this is concave up. All right? So if I were to fill in the blank from before, f prime is the slope, f double prime is the, I would say, concavity is the noun version of that. The concavity, be it concave up or concave down. It represents, is the general shape of it like a smiley or the frowny? That's the difference between concave up versus concave down. All right, let's just do one quick example looking at a chart. So a typical question that is usually fairly easy is I show you a graph and then ask you, where is this function concave up versus concave down, right? In the past we've talked about where is this function increasing or decreasing, but we can also ask about the concavity. So here is a graph. I'm going to try to draw this fairly specifically here. Something like that. So your job, give me intervals of x values where it's concave up versus down. All right? This, in my opinion, can be easy to confuse with increasing, decreasing. So if this was instead a question about increasing, decreasing, don't write this down, but because I'm about to undo all of this. If it were increasing, decreasing, you would look at these three special points and say increasing, decreasing, increasing, decreasing, right? But what I'm asking is not about that. I'm asking about frownies versus smileys, right? It's not about that same thing. In my opinion, I see one smiley region in the middle, right? The curve has this shape to it. Now, where exactly is that? I mean, it's certainly here. I would say, and you have to, I mean, it's kind of a judgment call. You have to say, where does this smiley continue to? I would say until around here, because to the right of that point, it switches to a frowny, right? So I'm trying to look at precisely where is the smiley region. I would say to around there, and going to the left, maybe around there. So in this region, it has the smiley shape, that is the concave up shape. And then further to the right, it switches to being the frowny shape. So over here, I would say this part here is down. And similarly, on the left side, that's the frowny shape, like that. This is also down, all right? So this is how you would identify these regions on the picture. To say the answer, I said give me intervals. Okay, so I can write those in terms of intervals. I would say it's concave up on the interval 2 to 4, right? This is 1, 2, 3, 4. And then down on minus infinity to 2 and 4 to infinity. Right? That's how we do it. The next thing to discuss is how to do this without looking at the picture. If I just give you an equation, can you answer the same question? That is quite a bit harder, and maybe we'll leave that until after this.